Okay, good afternoon. Let's start. So last time we looked at elliptic curves, right? Elliptic curves are curves of this form, but the general form is the top one. But we will mostly use the simplified form. Y squared is equal to x cubed plus ax plus b. We are going to use this simplified form. Y squared is equal to x cubed plus ax plus b. So if we use these two parameters, then the curve is defined, fully defined. So we can use some Sage math to draw the curve. We have to just give the parameters a and b. If it is in the longer form, then we have to give a1, a2, a3. Sorry, a0, a1, a2, a3, and a4. Right. Okay. The elliptic curve is something like this kind of curve, and there are many forms of that. We can define a group over the elliptic curve. So that's the important thing. So we have seen that when we do the public key and cryptography, we have used a group, mod M, right? Mod P group. Here again, we can define a group. There are simple rules. So we can take a point P on the curve and another point Q on the curve. Then we can add them together, right? So the curve is like this. So we have point P here, and then maybe another point Q over here. Then I'm really bad at doing things. Let's see. So it's like this, something like this. Yes. Then we have a point P here, and the point Q here. Then you draw it like P, Q. These are just xy coordinates. Points are defined by the xy coordinates. And then it intersects the line, the curve again at another point. Then we draw a vertical line across that. And this point is the P plus Q point. That is how it is defined. It is not like you take the x coordinates of this one and x coordinate of this one, and you add this together. You won't get this one, right? It is the points. This point is and this point. Take these two and draw a line, and we define this point to be minus P plus. And our zero, now if you add these two together, then you should get a zero. So our zero is at the infinity, right? So that is how these points are defined. And if you want to add P to P, then you have to draw a line that touches P and a point slightly away from P, right? So that line is the tangent at P, right? So again, in this drawing, it's not going to cross the curve here, but if you draw a tangent to any point, then it's going to cross the curve again. If you draw the elliptic curve properly, that's going to happen, right? So actually over here, the P plus P is going to be 0 in this point, right? So this is how the points, the group is defined. We have the closure property, right? You can see that if you take any 2 points and add them together, you get a point on the curve, right? So you have the closure property, and you have a 0 point, and you get additive inverse, right? For each point, there is a minus point as well, right? So we can do this now. We can actually, given the coordinates of this point, this is the x coordinate of P and the y coordinate of P, and we have the x coordinate of Q and the y coordinate of Q, right? Then let's call this point R, this point. Then the R has the coordinate XR, YR, right? Then that means the coordinate of this point, it is symmetric over the x-axis. This is the x-axis. So it has the same x coordinate, right? So this point has XR. What is the y coordinate? It is the negative of this. It's on the other. It is on the other side of the x-axis. But since it's symmetric, these distances are the same, right? So then other coordinate will be minus. Yeah. If this is yr, then that is minus. Yeah, this point, right? So then we can. So these are the only things that we know. We know this thing. We know this point. Then the question is, what is x p plus q? Then we should be able to find this point R. Okay. So I'm just going to draw the line. So we have a point P here, point Q here, and over here, this point has XR minus 1. Right? Okay. Now the gradient of this line, delta, is equal to YQ. Right, the other way around. That's YQ minus YP divided by XQ minus XP. Right? Doesn't matter whether you write it the other way around as well. You can write it as YP minus YQ, XP minus XQ. Both are the same. Right? Actually, this is also equivalent to let's say YP minus the y coordinate of this one, but that point is minus yr. YP minus yr divided by XP minus XR. Right? Okay. We also know that this is also given. Y squared is equal to x cubed plus ax plus b, and we can write the equation of this line as, since this is delta, y is equal to delta x plus theta. Right? P, Q, and this point, this is not R. Maybe I'm going to call it, let's say K. Point K, they are all on the line as well as the curve. Since these two are on the line as well as the curve, at these 3 points, this equation is true. This equation is true as well. Both are true because they are on the curve as well as the line. So we can actually take y from here and plug it in here. Right? If you do that, then we get delta x plus t square is equal to x cube plus ax plus b. Right? Then if you rearrange this is what we are going to get. X cube minus, you get delta square x square here. Delta square x square. From this we get c square. Sorry, let me expand this. Delta square x square plus 2 delta x c plus c square is equal to x cube plus ax plus b. Right? So I can rearrange that, bring these terms to the other side, and I'm going to erase this. And I get this equation in this form: x cube minus delta square x square plus a minus delta a minus 2 delta c x plus b minus c is equal to 0. So this has x cube, right? This is a cubic equation, right? So the general form, and since xr, and it only has x, there's no y. These are the equation of x, and we know that xp is there, x cube is there, and xr is there, right? These 3 points, xr, x cube, and xp, all should be should satisfy this equation, because I have got this from combining these two, the equation of the line and the equation of the curve, and these 3 points are the points on the both of the line and the curve. So this, if I plug in xp here, it should satisfy this equation. If I plug in x cube here, it should satisfy this equation. If I plug in xr here, it should satisfy this equation. So such an equation can be written like this: x minus xp into x minus x cube into x minus xr equal to 0. So xp satisfies this equation. Plug in xp here. This is 0. You don't care about the others. Once this component is 0, the whole thing is 0. So xp satisfies this equation. It should satisfy this equation as well. X cube satisfies this equation. It should satisfy this equation as well. So essentially, these two are the same, right? Actually, you can multiply this whole thing by a constant factor, then it still has the same effect. So these two are the same up to a constant factor, right? So then I'm going to expand this. I can expand this equation. When I expand this equation, I get a longer one. I'm not going to write the whole thing. But if I expand this, there's some term here, x cube term here. And I have this term, xp plus. I'm not going to write the whole one. X cube, xp plus x cube plus xr into x square. Then a bunch of others equal to 0. This is also equal to 0. Now, since these two are essentially the same equation, then this component delta square should equal to this one. Why? This is the constant in front of x square, and this is the constant in front of the x square, right? So these two should be equal, right? Otherwise, then the x square term here has a different meaning than x square term here. So these two should be equal. This thing minus delta square should be equal to this, right? From that, we can directly get the value for minus delta square. By the way, this sign is also minus, this sign is also minus. Then these two should be equal, right? So I'm going to erase this whole thing again. And write that equality. Delta square is equal to xp plus x cube plus xr. Right? From this, we can get xr as I can keep XR over here and on the other parts here. That is delta square minus XB minus XB. So now I fix because this I can calculate. I only need YQ and YP, XQ and XP. I know those, right? So I can calculate that. So I know this, I know this, I know this. Therefore, this is the unknown one. I can calculate, right? Okay. Now, so I know XR. Now this is equal to delta, right? This thing is equal to delta, and I can write that this is delta because this is delta, this is also delta, this is delta, this is also delta. So this is YP plus YR divided by XP minus XR is equal to delta, right? Therefore, YP plus YR is equal to YP plus YR is equal to delta into this thing, XP minus XR into equal to delta into XP minus XR, right? So that means YR is equal to minus YP minus plus delta into XP minus XR. So now we know YR as well. We know YP, this is minus YP. We know YP. We know delta. We know XP. We have already calculated delta, right? So we know all the parameters. So we can get YR as well, right? Okay. Now that is adding 2 points. That now two different points. But if I want to add the same point to itself, then I have to find the tangent line, right? So again, then the tangent line at a point, say this point, tangent line at this point. So there are no 2 points. If I have 2 points, then I can write the equation of this line and follow through the previous step. But now I don't have 2 points. I only know that it's a tangent. I know that fact. So then we can take the equation of the curve, that is y squared is equal to x cubed plus ax plus b. So far, I have used only maths up to the 8 levels, right? So here I have to use calculus, right? So don't worry if you don't know much about calculus, but I can calculate that delta for the gradient. Gradient is this thing. I can calculate it from this equation. It's going to be, if you know a little bit of calculus, then you can follow this. It's going to be 2y dy by dx is equal to 3x squared plus a. 2y dy by dx is equal to 3x squared plus a. Right? From this is delta. Delta is like this. 3x squared plus a divided by 2. So if you know that, then again, we can use the same equation, this equation, but over here, xp is equal to x cube. So this from the equation 6, I get minus xp minus x cube. So this becomes minus 2x cube. Right? So that is, it is delta square minus 2xp. So over here it is xr is that delta. We have calculated that square minus 2x. Right? Similarly, y over here, yr is minus yp into delta into xp minus xr, right? So we can do this as we can calculate this as there's no q here, so that's okay. In the second equation number 7, there's no q, and we don't have a q right now. So the second equation is the same in this case, since there's no q there, but delta is going to be different, so we can get yr as well. Okay, this is the way we do addition on an elliptic curve where these parameters are coming from real numbers. They are real numbers. It is also real. One, but it's a real number, considered as a real number. But we are interested in this works. This is a group. It works. But we are interested in doing these calculations mod p. Right? For example, we can take this equation again. Let's take one particular elliptic y squared is equal to x cube plus x plus 1. That is one particular elliptic curve, right? That is what you have drawn here. It is this curve, this particular curve. And now we want to take the same equation and do all the calculations mod, let's say mod 23, right? So if you take the point 9,7, we can show that it is on this curve. If it is on this curve, then y coordinate is 7, x coordinate is 9, then y square, that is 7 square, should be equal to x cube, that's 9 cube, plus x, that is 9, plus 1, mod 23. Right? So what is 7 square? 49. What is 49 mod 23? Yes, 3, right? So this is 3. And 3 should be equal to 9 cube plus 9 plus 1 mod 20. Just to make these things easier, I can write this as 9 into 9 mod 23 into 9 mod 23. Remember that we can write it like this, right? Plus 9 plus 1 mod 23. What is 9 into 9? 81. What is 81 mod 23? 3 times 23 is 69. So remainder is 12. Right? So this is 12 into 9 mod 23. 9 plus 1 is 10. 10 mod 23 is 10. But we do have to do all the calculation mod 20. Right? Okay. 12 into 9 is 108. Right? What is 108 mod 23? 4 times 23 is 92. Then 108 mod 23 is 16. So this is going to be 16 plus 10 mod 23. That is 26 mod 23. Yeah, it is equal to 3. So these 2 points satisfy this equation mod 23. Therefore, these 2 points are on this elliptic curve defined over mod 23. Right? So it would be good if you can use Sage. So type these commands on the Sage. A field defined over 123 is called a Galois field. Remember that I just mentioned that GF23. Type the command and you can get the elliptic curve. Elliptic curves over Z20. There's a typo there, Z20. Did you get the curve? Okay, that's all. You can type this command on Sage and try it. Why do you get an error message or you have to type the function name as it is, like you cannot change uppercase to lowercase one. Do you have the Sage installed on the machine? Spelling mistake, yes. Got it? So this curve does not look like our original elliptic curve at all. Bunch of points. It's not really a curve. So we don't have infinite number of points on the curve. We have only finite number of points, right? But still, even though it doesn't look like a curve, these equations hold, right? If we know the coordinate points of any point P and any point Q, we can calculate the coordinates of the point R, right? Using the same equation. Right? But important thing is that we only have finite number of points here. Okay. Let's move on. Yes. Yes. Maybe, do you get the same error? You can also try it on the web. It should work. Yeah, I have tried it on Sage here. So, yeah, maybe Sage has some issues. Right? I tried it on Sage. This is what I got. So it should be like this. This is the command. Equals elliptic curve, then you can plot it. You can also type this command and get the points. So these are the points on the elliptic curve. So don't worry about the format. It is using 3 coordinates, right? This is called the homogeneous coordinate system, right? But you can easily omit the last coordinate, number 1 there. You can omit that. Then you get the regular XY coordinates. The coordinates are given in homogeneous coordinates because there's no other way to define the point at the infinity, right? So just to define the point at the infinity, or this point, actually, 0 point, right? We use the homogeneous coordinates. So we can get the points on the elliptic curve, and you can see that they are finite. Only finite number of points are here. Okay. Now we can define RSA-like algorithm on this curve. Elliptic curve cryptography. So here, elliptic curve, the addition in the elliptic curve is like corresponds to the multiplication in RSA. Then the multiplication in the elliptic curve is like the modular exponentiation in RSA. Right. So multiplying a point by k times is adding a point to itself k times. So when you do the first addition, have the curve. Then let's say that this is point P. So let's say I want to find 3P. So first I have to add P to P itself to get 2P. So that is to draw, first I have to draw a tangent across this. So this is going to cross the curve here, then you come up with 2P point here. Right? Then to get the 3P, you have to draw a line from this first point to this point. So it is going to cross the elliptic curve at some other point. That is 3P. Then to get 4P, you have to connect this point, that point with this P. Right? You have to keep on doing that. Right? So then you can calculate any KP or given K. Right? So if you know KP, this value of this thing, and maybe you know P as well, but there's no easy way to find this K. Right? You have to keep on adding until you come up with the right value. Right? It is like discrete logarithm. Right? But this is again much harder than discrete logarithm when we do it mod P. Right? But the forward question is easy. If I know P, if I know K, it is relatively easy to find K into P. Right? You can do this calculation. But finding K is not easy. Right? Then I showed you this, that you can get the elliptic curve and then you can get the points. When you calculate the elliptic curve modulo 23 or some other prime number, all points are not on the curve. Some points are on the curve. There are a finite number of points. So if you want to use this system to encrypt messages, first you have to represent messages using points on the curve. Right? So you need some kind of encoding that maps the message into these points. So if you have, if there are only 100 points here, then you can only send 100 messages. So there must be some way of mapping messages to these points, right? So if you take the message as a simple binary string, so it is just an integer. You can get it as an integer and you can do RSA on that. But now you have to map it to a point, xy coordinate, right? So we can only pick finite number of points on the curve, and then we have some way of doing this mapping. Right? There are efficient way of doing this mapping. So I'm not going to go through that, but we need that. So you cannot treat the message as a simple number now. You have to have this mapping. So you can convert it into a point on the curve. Can you try this as a? So first get the curve, and then you can define points on that curve. P and Q. P is 0.310 and Q is 0.97. Then you can find out what is P plus Q, what is 2 into P. On Sage, you can do that. That's one reason that we are using Sage here, right? Otherwise, we cannot do these kind of calculations. Got it? Okay. So this is how we do the Diffie-Hellman key exchange. So then first we have to pick a large prime P and curve parameters AB. So once you know the parameters of the curve, we can define the curve. Elliptic curve is y square is equal to x cube plus ax plus b. These are the curve parameters, right? So we have to pick these parameters and we have to pick p as well. So p, once you pick p, then we do all the calculations on p, right? And this whole equation actually, these are a, b, and p. If you know these three, we know this curve, right? This is going to be public. Elliptic curve E, that is going to be public. And then we have to select a base, something called a base point, G. It is a point on this curve. So there are finite number of points here. We have to pick one point out of that. So that point has a special property, so that if we keep on adding that point to itself, G plus T, you get 2G, right? Then you get 3G, 4G, 5G, and NG. So at some point, it is going to be 0, right? Remember that when we select parameters for Diffie-Hellman key exchange, we consider the order of a point, right? We pick a number and we were interested in the order of that. So if we keep on multiplying that number by itself, at some point, it is going to hit 1. But before it hits 1, it should go through all the numbers, right? Likewise, before this hits 0, but once it hits 0, it's not going to change, right? If ng is 0, n plus 1g is again 0, right? Before it hits 0, it should go through all the points, in some order, right? That means it covers all the points, right? So we have to pick g like that, or at least this n has to be really, really large, right? Then we make this public, and the g public as is also public. Okay. Now we have Alice and we have Bob. Again, Alice has to pick a private key or the secret parameter. That is, let's call it NA. And then Alice calculates NA into G. Right? And this is sent over the public line. So the NA into G, that goes over the public line to D. So D is going to have NAG. Right? So whole world can see that. They know G, they know the elliptic curve, but they cannot figure out NA because it's difficult. Right? Then B also fix NB is private parameter and then calculates NBG. And this is also sent over the public line into Alice. So Alice gets NBG. So when I write something like that, don't think that Alice knows NB actually. Alice knows the net result of this, not the individual parameters. Right? Again, it's the same thing. Bob knows the value of this, not the individual parameters. Sometimes we may get confused because it looks like Bob gets to know about NA and G. No, Bob gets to know about the NA into G, that final value, final point, not these parameters. Right? Okay. Once Alice gets this, Alice multiplies this by NA. Right? So Alice gets NA into NB into G. Right? So the Bob got this, and Bob is going to multiply this with NB. So Bob is going to get NB into NA in G. So that is NB NA G. So this one is equal to this one. Right? So this is the agreed key. This is the DPL1 key exchange. Okay, let's see how we can do the encryption. Yeah? To encrypt, first task is to represent the message as a point on the curve, right? So let's assume that the message is encoded as this point, EM. And then A has a private key, right? So Alice has a private key. Say this is Alice. Alice has a private key, and private key is NA. And Alice also has a public key. Public key is point PA. Remember, these are points. Point PA calculated like this, NAG. Right? As in the DPL1 key exchange. Right? B also has a private key and the public key. So this is Alice. This is Bob. Bob has the private key NB and public key EB is NB into G. So let's say Alice wants to send a message to Bob. So Alice has to consider this letter. Construct the site X C C of M is equal to A into G plus A into G, A into G, E M plus A P P. Complicated. So Alice picks a random number just for this encryption, right? So Alice multiplies PM. Alice multiplies PM by kg, right? PM by kg multiplies PM and kg, and then also add k into PB to that. K into PB to that. Right? Is that okay? Kg into PM and K into PB. This whole thing is the encryption. Then Alice sends this to Bob. So Bob gets CM. Second. Encryption is like this. Actually, K into G, comma, EM plus A B. Actually, earlier form should be wrong because I have multiplied kg with PM because kg into kg is a point. So I have multiplied a point by a point. That is not defined here. But this is defined. K into G, that's a point, right? So it generates a point. PM is a point, and K into PB is a point. You can add these two points together, right? Okay. Then when Bob gets these two parameters, K into G and as well as this, right? So Bob get this part, that is PM plus K into PB, right? And take this one. Remember again, Bob does not know K. Bob knows only K into G, right? So Bob takes this and multiply it by NB. Bob can do that because this is Bob's secret key. So Bob multiplies this by NB and Bob NB to get this NB into KG, right? Then Bob subtract this from this point. This is the encryption of the message. This is the extra parameter that Alice sends to help to decrypt it, right? Okay, so let's expand this. So this has PM, that's the message point. Again, remember, others cannot get, or even Bob cannot get PM out of this. This is the total point. This is a point. Point is this total addition represents 1 point. You cannot extract PM out of that, right? So we get that point, whatever that point, that is PM2. K into PB. But what is PB? Public key of Bob. Public key of Bob is NB into G. So this is K into NB into G. Now Bob is subtracting this number, NB into K into G. These two are the same. They are points. Not numbers, points, but they are the same. So you are subtracting a point from itself. So you should get the 0 point here. So this is equal to PM plus the 0 point. So this is equal to P. So Bob can get back the message point. Then again, Bob has to do some kind of decoding to get back the message. Because the message is already encoded as a point on the curve. Is this okay? Okay. So that is the end of our discussion on public key systems, right? So now let's go back again to the Caesar cipher, right? In the Caesar cipher, let's say I have a very long text, maybe like a book, right, one large book, and I use some key, Caesar key, and encrypt this whole thing, right? And this encrypted text is available to you. Can you suggest an easy method of finding the key rather than going through the whole 26 keys? Some way of figuring out the key. So this cipher is, it's a very naive cipher, but to illustrate certain points, we can use it, right? So this point, it's very trivial to use this cipher to illustrate the point I'm making, but it's the easiest one to use, right? So you have this text, cipher text, nothing else. So rather than trying out all possible keys, can you suggest a method to figure out the key? Can you analyze the cipher text and figure out the key? So that kind of action is called the cryptanalysis. Can you do that?
We can check for the patterns, which letter is appearing more times and something like that.
Yes, good. Yeah, that's a good answer. But what kind of pattern?
For example, in English, if it is English, the letter E is appearing a lot of times.
Right, excellent. So if you know that it's English, right? If it's English, if you know that it is English, we can rely on this. If you have a large corpus of English text, and if you calculate the frequency of each letter, right, you get something like this. We don't use all the letters with the same frequency. So letter Z is hardly ever used, right? Most used letter is E, right? So now if I know that you have used Caesar cipher, what happens is each letter get transposed into some other letter, right? But letter A get changed into, say, some letter, say P. So everywhere the letter A occurs, you find P, right? That's constant. So if you figure out the most used letter in the cipher text, maybe let's say it is L. So that means L is E. Right? If you know that L is E, then if you can guess that, then you know the distance between E and L, and then that is the key. So you can use that fact to get the key out of it, right? So even though C cipher is a very trivial one, this illustrates bit of a hole in the crypto system, right? So okay, so then why can't we use say 2 letters at a time? If you use 2 letters at a time, then we should be better off, right? Okay, so one way to use 2 letters at a time. So this is one way of doing this. This is called the Playfair cipher, right? So in the Playfair cipher, you have a key, and the key is represented as a 5 by 5 square. So key is Playfair example. So that is the key I'm going to use. Playfair example. So to construct the key, first you take this string, Playfair example, then you have to write it in a 5 by 5 square, right? So keep on writing these letters, play, P, L, A, Y, then F, play, fair. After that, play, fair, FA, but A is already used, so skip that. Right? So the letters in red, those are the skip letters. So then we use I. Yeah. Play fair. X, sample, E, X. A is already used, right? So we don't take it. M, right? Then P, L, E, A, again used, right? Then after you have done that, so all whole thing is done. Then after that, you write remaining letters. A is already used. There's no point in writing that. Then you write E, then C, right? Then D, E and EF are already used. Then G, then H. For I and J, we skip that. I is equal to J and we skip that. Reason is this is a 5 by 5 script. There are only 25 places. So we cannot write all 26 letters, right? So we take J is equal to I, right? Then K, L and M is already used. N, O, P is already used. Q, R is already used. S, then T, U, T, U, V, W, Z. So this is the key, right? Then we use the key and then use bunch of rules, right? So these are the rules. So first you take 2 letters at a time and then enter, right? These 2 letters are called bigrams, right? 2 at a time, then they are called bigrams. So we take a bigram and code that into another bigram. So hi, HI, right? If you take that, these are I is over here, H is over here. So it's in a 2 different corners of a square, right? So instead of these 2 corners, we use the other 2 corners, right? P and M. For to the decryption, if you get these 2 corners, we know that original text is I and H, right? So this is one rule. So if you find letters in the same column, like D, E, sorry. Yeah, E, yes, D and E. For you use the one immediately below that. For D, you use O. For E, you use D. Actually, this is not really secret cipher, right? But it has a bunch of rules like this. Again, for T and H, T is over here, H is over here, 2 corners. Then you use the other 2 corners, right? Again, the corners can be like this: E and G on this. right? They have two corners, so use these two. So it can be like this as well. Oh yeah, right? And it can be in a row, right? In a row, you use the immediately one immediately to the right. So E is encrypted as X, and X is encrypted as M. Right? Yeah. So we are done. Now we should not see E always getting translated into certain other characters. For example, in here, X, E get translated into X. If you have D, then E get translated into D. So the same E now get translated into different characters. So we should not see that kind of pattern. That, yeah, still E is the most used letter, but in this encryption method, E get translated into different characters. So we should be safe, right? Not really, because people have found there are bigram frequencies as well. These are the bigram frequencies. Right? So you take two letters at a time, and there are certain patterns, certain frequencies. There are bigram frequencies. Then we can use trigrams, but still there are trigram frequencies as well. Now you can see that here the curve is getting a little bit flatter. Ideal one is the total flat curve. That means each component is represented equal. Then there's no pattern, right? So if you look at the letter frequencies, they're like this, drastic differences, right? Individual letters. But if you take bigrams, it has flattened out a bit. It has flattened out a bit. So if you use a trigram, it will get flattened out a bit. So if you get n-gram where n is 100, then we can have a much flat curve, much more flat curve. But still, you can figure out certain patterns, right? Okay. So then again, I will just explain one more cipher. So can you see this? Let me expand this. Yeah, this is called the Wigner cipher. So this is the table for the Wigner cipher. So the over the top row we have letters A, B, C, D up to Z, and in the first column we again have the same letters. In the first row within the table, like the first one can be considered as the headers. First row within the table, you have A, B, C, D, E, F, similar to the first row, headers. And then in the second one, they are shifted. And in the third one, they are shifted by another. And so on, right? So when you come to the last one, so everything is shifted by 26%. Right? So we take this table and then to encrypt a message, let's say that our message is P, and we skip spaces because there's no encryption for spaces here. So our message, plain text say, attack at dawn, right? We take the plain text and we take a key, which it should be as long as the plain text. But in this case, we don't have a key like that. So we are going to use the key called lemon. Lemon is the key. So we repeat it as many times as we want until we can cover the whole plain text. Right? So we can write the key multiple times, repeat the key right underneath the plain text so that it covers the whole length of the plain text. Then we take we take the key letter, for example, L. So then we go to the row that is starting with L. That is this one, right? This row. Right? And then we check we go to the column that has the plain text. Go to the row that has the first letter of the key, L, and go to the column that has the first letter of the plain text, that is A, and then get the corresponding slot in the table, that is L again. So that is the encrypted value. Right? Then let's go to the second one. Then the key is E. So we go to the key, row that has E there, starting with E. Then we go to the column that has T there. What is that column? This one, right? Yeah. So then the encryption value is X, right? So if you go through this, say the first A got translated into L, right? First A got translated into or encrypted into L. Can you see that? But if you look at this A, this one, second A in the plain text, it got translated into O. And the fourth A there, it got translated into E. So each letter, same letter, get translated into different characters, right? So then it looks like we have lost all the identifying marks in the ciphertext. It is true, but there's a glitch here. Can you figure it out? Same as the? Not really. That is for the A. Yes. A, same as the key letter. That is not really a, since we don't know the key, attacker doesn't know the key, so attacker cannot figure it out. But there's going to be a problem. Problem is, let's take so we have the plain text. So long string of characters, plain text. And we have a key. Actually, key is really small, right? Not really small, but compared to the plain text, it's going to be small. So what you do is you repeat this. You repeat the key. Right? So if the key, the first letter of the key, L, then that determines the translation of this character. This key letter determines the translation of the character because we are using that particular row to do the translation. Right? Is that okay? So over here again, over here again, right? So we have used lemon, right? Lemon, L-E-M-O-N. So 1, 2, 3, 4, 5, and sixth one again L. Right? So again lemon, L-E-M-O-N, 6, 7, 8, 9, 10, 11. Right? 11 one is again L. So this is a 6th one L, first one L, 6th one L, 11th one L, and the 16th one is also L. Right? So these are like, if you take this one, just this one, and this one, and this one, and this one, that is exactly like Caesar cipher using this key. Right? All these letters get translated using the same row. So it is one row is like a six cipher, right? So if you can guess the length of the key, if you can guess it somehow, then if you take first letter, sixth letter, 11th letter, 16th letter, and so on, every fifth letter in the ciphertext, that shows exactly the characteristic of the normal English text, right? Then you can figure out that. So then from this point onward, the second, 7th, 12th, and so on, they have the same characteristic. So now you have several sets of English plain text like characters. Right? So you can apply this and get back to that. Right? So it looks like that we have hidden the key, but not so. Right? But there's a way out here. So we have a long plain text. And if we have a very long key, which has the same length as the plain text. So this is key, this is the key. Right? And then there's no pattern like that. So this is a very long key. And let's say that we picked it, it's not an English word like lemon. It's a random string. Right? We have a very long random string. And then text. Then we do the translation. It doesn't matter whether we use the Wikinger cipher or the Playfair cipher, or using this one, it can even be a season, right? Or if we consider this plain text as just ones and zeros, these are ones and zeros, long string of ones and zeros. This is also a long string of ones and zeros, right? So you can actually use addition of these two mod 2. Addition of this one and this one mod 2. Actually, mod 2 addition can be easily done using if I call this A, if I call this B, A exclusive of B, right? So that is mod 2 addition, right? So if you do that, then we get sort of a random string because this is random, right? So this is the best encryption, right? Ultimate encryption. This is called the one-time pattern, right? And you cannot use this string again to encrypt anything else. If you do that, if you don't use this string to encrypt anything else at all, and this string is created entirely randomly, right? And generating random numbers is not going to be easy, right? Why? On a computer, it's not easy to generate random numbers. Why? Any idea? On a machine, on a computer, it's not easy to generate a random number. How do you generate a random number? Using a program, right? Algorithm. That means it is deterministic. If you know the input, you know how it gets translated, right? So the random number generation is not really easy on a computer. Right? Then you have to depend on some random event, right? Take the current time, and so CPU speed, current time, number of processes running, and combine them together. Again, that's not really going to be random, right? If you want this for really cryptographically secure cases, then you have to use hardware random number generators. They cost few $1 million, really good ones, right? They may take some parameters like transition of an electron between certain energy levels and so on, right? So that kind of randomness. Otherwise, if it is not really random, then this is not going to work, right? Because if you know the process of generating those numbers, then you can guess this. And by the way, Means reality so let's say number 23, 5,295. Which one is more random? And number 10 is. Which one is more random?
And 23.
Which one?
Both the first one and second one.
First one and the second one. Why?
Yeah.
Why they are more random?
Because there is no repetition of numbers, but in the third one there are 2 5s.
Okay. Okay. Yes, that's one way of looking at it. But actually, there's no meaning of asking the randomness of these numbers because the randomness depends on the process of generating that number. Right? So you can claim this number 23 is more random, then if the next number I'm going to write is again going to be random, then 23, then the next number is also 23, then this is going to be really predictable. Right? So randomness is actually coming through the process of generating. Number itself, there's no meaning of asking the randomness of that. Even an isolated number, right? There's no point in asking about the randomness of that, right? So the randomness depends on the process, right? But that was a good observation, that having 2 5s there. But that does not really reflect the randomness of this. Maybe to another base, this may have 2 1s at the same place. Say base 2, this may have 2 1s at the same place, but not on this one, right? So maybe in another base, they may have a different pattern. But that is not the randomness. Randomness is the process, right? So I generated them. So I have in my mind to generate 23 over and over again after this. Right? So then it's not going to be random. Right? Okay, so we'll later on look at random number generation. So if you have a very long random number as the key, yes, that is the ultimate security, right? But that is not going to be practical because for the sender that is okay, right? Sender can create a long random string and encrypt the message. But how can the sender send that number, random number, or the key to the receiver? And for each message, it has to be different. So it is like another message itself. Right? So that's not going to be really easy. It's almost impossible unless you have a code book at 2 different places. For a certain time in the day, use one, you go to the code book, pick the row, maybe depending on the time or some other parameters, and that is going to be your key. So the sender and the receiver, they both do the same thing, right? Then it is going to be really secure, but again, not the ultimate security. It is not the ultimate security because you have some process of determining that string, and that is already decided. So it's not really random, right? Okay, so that is what we want ultimately. Okay, so this is not easy. Playfair cipher, yes, we can do that, but still we have the bigram frequencies. Big-near cipher, still we can break it if you know the length of the key, or if you can guess the length of the key. What you can try is, you can try different lengths. And the length that gives you the pattern of E is the length of the key. Right? You are looking for the pattern of E. Right? That is exact. If you can find that pattern by changing the length, and then you can figure out the length of the key. Once you figure out the length of the key, then you can figure out each letter. Okay. So this is another way of trying to do this. Can we list the encryption as a set of linear equations? So I'm going to use this. So what I mean by set of linear equation is let's take 4 parameters A, B, C, and D, 4 parameters, and then our plane text, right, can be P1 and P2. So first letter of the plain text is P1, second letter of the plain text is P2. So I can multiply P1 by A into P1 plus A into P1 plus B into P2. This is say X, first letter of the ciphertext, X1. So the first letter of the ciphertext is coming from 2 different plain text letters, right? Kind of like a bigrams, right? And the second letter of the ciphertext is coming from C into P1 plus D into P2. Is that okay? First letter is A into P1. We are still encrypting just 2 letters. And we are getting the first letter of the ciphertext and the second letter of the ciphertext. So the first letter of the ciphertext is A into P1 plus B into P2. Right? And maybe we do this mod P. We can do, but for the time being, let's forget it. Second letter is C into P1 plus D into P2. Right? Is that okay? So I am going to use a different notation now. Maybe you are familiar with this. Are you okay with the matrix notation? Matrices. Heard of matrices? Right? So there's a different way of same thing, same stuff. There's a different way of representing this. Way of representing this is I can write this A, B, C, D, and P1 and P. So this gives me X1 and X2. These are these 2 set of equations. These 2 equations can be written concisely like this. What you have to take is take this column and take the first row and do the multiplication. Take this column and take the second row and do the multiplication, and you get the answer. Right? So here I have combined 2 letters of the ciphertext by taking different proportions and create the first letter of the 2 letters of the plain text and created the first letter of the ciphertext. Right? So this is the way to do that, and this is one way of representing that. This is much more concise, simple, right? But only thing you have to know is how to do the matrix multiplication. Take the first row and this column, multiply them together. A into P1, P into P2. That is this one. Right? C into P1, T into P2. That is this one. Right? Rows are multiplied by columns to get one value and add them together to get a one value. Right? So this is another way. This is one way to represent this. Right? Okay. Now, if you want to combine more, then I can have I'm going to write it in a different way. A11 into P1 plus K12 into P2 plus K13 into P3. If you want, you can have K14 into P4. So here I am combining 3 plain text letters. Right? You can have 10 ones. But for each one, you need a key But these three again should be combined in a different way to get the next one. So 3 plain text letters should give me 3 ciphertext letters. But this line gives me only 1 ciphertext letter. Right? So to get another one, I need another set of keys. K 21 into P1 plus K 22 into P2 plus K 23 into P3. Then this gives me the second ciphertext letter. Okay, third one, because we have 3, then I should get 3. So third one, K 31 into P1 plus K 32 into P2 plus K 23 into P3. Right? So I get the third. So 3 set of equations. Actually, these are called linear equations. 3 set of linear equations. Again, this can be concisely represented in the matrix form. In the matrix form, I have A11, A12, A13, A21, A22, A23, and A31, A32, A33, right? Multiplied by P1, P2, P3. And I get X1, X2, X3. Right? Maybe if you are doing letter by letter, then this combination of the letters should give me a letter. Right? But if you multiply, if it's, let's say P3 is Z, that is 25. Then 25 is, maybe this is 2, then 50. Then already it's not a letter. Right? So we have to do all this calculation. Mod 26. If we are taking letters at a time. Right? So all this should be mod 26. Mod 26. Then this should be mod 26 as well. Otherwise, we don't get a letter. Right? We get a large number. So that's not meaningful in this context. Right? So because I have to translate a letter into a letter. Right? So this is another way of doing this. Right? And this type of cipher, this is called Hill cipher. Right? Okay. Maybe let's take a break. Right? And when we come back, you have to encrypt using Hill cipher. Right? To do that, you should be able to represent matrices in Sage. So in Sage, this is how matrix is represented. Matrix. I can have, if it is, let's say, A, B, C, D. If this is the matrix, in Sage, you can write it like this: A, B, first row, comma, C, D, second row. Then this represents the whole matrix, and that's it. But if you want to do the mod 26 calculation, then you have to write it like this. Instead of A, you have to write mod A 26. This one also mod, right? So yeah, let's take a break, and after the break, let's do this.